suck at calculus? Is there difficulty in understanding the depth that lies within the extreme value theorem, Rolle's theorem, and the mean value theorem? Well, if so, then you came to the right place, because today we're going to provide you, America, with the best materials that will allow you to fully grasp and comprehend the necessary information that encompasses these irritating, annoying theorems. So now we're going to give it over to Dakota with the extreme value theorem.
Well, thank you, Hayden. Okay, first off, before we get started on extreme value theorem, there's two major things you need to know. First off, what is an extrema? Well, it is an extreme value on the function on the interval. It is also known as the maximum or minimum point. The number at which these points are found is called the critical numbers, which you find by setting your derivative equal to x. Okay, the extreme value theorem. If f is continuous on a closed interval, a, b, then f has both a minimum and a maximum on the interval. When using the extreme value theorem, you're searching for a relative max or a relative min. You could say that the relative maxes occur on hills, while the relative min occur in valleys. Alright, so the definition of a relative extrema is as follows. If there is an open interval containing c on which f of c is a maximum, then f of c is called a relative maximum of f. If there is an open interval containing c on which f of c is a minimum, then f of c is ruled as a relative minimum of f. Extreme value theorem. Okay, so we're going to do a couple examples for y'all now. Alright, in example 1, we're going to start off with f of x is equal to 3x to the 4th minus 4x to the 3rd on the interval of -1 and 2. Alright, so first off we're going to take the derivative. If you don't know how to do that, look closely. You're going to take your 4, which is your exponent, and multiply it by the number in front, which will give you 12x. Then you're just going to mark this down 1, and it will become 12x cubed minus, keep the sign, then you're going to take the derivative of this one, which will give you 12x. Mark that down 1, you'll get squared. And this is all equal to 0. Now what you're going to have to do, since a GCF can be taken out of 12x squared, greatest common factor, you're going to take out 12x squared, and what you'll have left is x minus 1. Okay, that is all equal to 0. So now since you have 2, you're going to have to find two different critical numbers. You're going to set 12x squared equal to 0. You're going to divide by 12. That will give you 0, because 0 divided by any number is still 0. So x squared is equal to 0. Now you're going to have to take the square root of both. So you'll still be left with x is equal to 0. So there's one of your critical numbers. Now your other one, you're going to take x minus 1, set it equal to 0. You're going to add 1 to both sides, which will give you x is equal to 1. Now what you're going to have to do here is you're going to have to go back and plug it into your original f function. We can represent it by this chart here. So you have f, and you're going to use both numbers on the interval. So f of -1, both your critical numbers, so f of 0, f of 1, and f of 2. So now what you're going to have to do is you're going to go plug all of them in. If you plug -1 into your original f function, you will come out with 7. If you plug 0 in, you'll come out with 0. You plug 1 in, you will come out with -1. And if you plug 2 in, you will come out with 16. So here's you look at it. On the interval, the absolute max is 16, but we're looking for the relatives. So your relative maxes, which will be your critical numbers, will be your 0, which will be your rel max, and your -1, which will be your absolute and your relative min. Okay, so now we're going to do example 2, and in example 2 we're going to show you how to find it when you're using a graph. Now the interval is 0 and 4, so your interval will be here and here. Now, as I said earlier, relative minimums and relative maximums can only occur on a hill and valley. So your relative min would be approximately 3. So you can say relative min is equal when x is equal to 3. Now, for your absolute, it can occur anywhere along the interval. So you will have an absolute min at the same exact spot for 3. Min is equal to x equals 3. Now for your absolute max, you're going to have to come all the way up here for 8. So your absolute max is equal to 0. And now to Tico with Rolle's theorem.
Dakota. I'm Tico, and I'm going to tell you about the Rolle's theorem. But first, I'm going to give you a little historical background. The French mathematician Michel Rolle first published the theorem that bears his name in 1691. Rolle was one of the first, most vocal critics of calculus, stating that it gave erroneous results and was based on unsound reasoning. Later in life, Rolle came to see the usefulness of calculus. So now on to Rolle's theorem. Rolle's theorem states that let f be continuous on the closed interval ab and differentiable on the open interval ab. If f of a equals f of b, then there is at least one number c in ab such that f prime of c equals 0. So there is a min or a max on the interval, and c is a critical number. And conclusively from Rolle's theorem, you can see that if a function of f is continuous on the closed interval ab and differentiable on the open interval ab, and if f of a equals f of b, there must be at least one x value between a and b at which the graph of f has a horizontal tangent. If the differentiability requirement is dropped from the Rolle's theorem, f will still have a critical number in the open interval ab, but it may not yield a horizontal tangent. Okay, so now we're going to do some examples that illustrates Rolle's theorem. For this example, it states that find the two x-intercepts of the function f of x equals x squared minus 3x plus 2, and show that f prime of x equals 0 at some point between those two x-intercepts. So the first thing we're going to do is just write out f of x. Okay, and then all we're going to do is factor this out first to find our x-intercept. So if you factor this out, you get it will be x minus 2 and x minus 1. And to find your x-intercepts, you find the zeros of these factors. So this one will be x equals 2 and x equals 1. So this is going to be your x-intercepts. And we're just going to write it like this. Okay, so the second step, you're going to take the derivative of f of x. So you take this to the front. It's going to be f prime of x equals 2x minus 3. And what you're going to do now to find this part, where it says and show that f prime of x equals 0 at some point between these two x-intercepts, you're going to take this derivative and set it equal to 0. The first step, you're going to add 3 to both sides. So then you'll have 2x equals positive 3. And then, to get this 2 off and get x by itself, you divide by 3 on both sides. Then you get x equals 3 over 2. And so, and then you just see and look and see if this number falls on your interval, and 3 over 2 does. So at x equals 3 over 2, f prime of x equals 0. And these are your two x-intercepts. So now we're going to do a second example that illustrates Rolle's theorem. In this problem it says let f of x equals x to the fourth minus 2x squared, and find all values of c in the interval -2 to 2 such that f prime of c equals 0. So the first step we're going to do is just write out our function. F of x equals x to the fourth minus 2x squared. Alright, now all we're going to do is just find our derivative. So f prime of x equals, we're going to move this out here, 4x, take this down to 3, minus 4x, that's it, just 4x. Alright, so now what we're going to do, we can GCF this. So we're going to take out 4x, and we're going to be left with x squared minus 1. And you can even break this down even farther and say f of x, or 4x equals x minus 1 and times x plus 1. So this is this same thing, just broken down even farther. So now what we're going to do is find the zeros of each one of these. So 4x equals 0. We're going to set that equal to 0. And you divide by 4 on both sides. So here, x is just going to be equal to 0. And then you're going to set this one equal to 0. You're going to add 1. X is equal to positive 1. You're going to set this one equal to 0 finally. Subtract 1 on both sides. And x is going to be left with negative 1. So you have 3 instances here where the derivative of this function is equal to 0. So real quick, I want to show you what this looks like graphically. Our little graph. You're going to have, it's going to come down right here and come back up. And so you're going to have a horizontal tangent line here, here, and here. And this is x equals negative 1, x equals 0, and x equals 1. And that's what this is going to look like graphically. And that is Rolle's theorem. Now to Jesse with the mean value theorem.
My name is Jesse Koslow, and today we are talking about the mean value theorem. The mean value theorem is if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a number c in AB such that y2 minus y1 over x2 minus x1, and the mean reverts to the average. Requirements for the mean value theorem is that f has to be continuous and f has to be differentiable. It always holds true that there is going to be a tan line and a secant line parallel. The alternative mean value theorem is if f is continuous on AB and differentiable on AB, then there exists a number c in AB such that f of b equals f of a plus b minus a f prime of c. The mean value theorem also ties in with the rate of change, which is the mean value theorem implies that there must be a point in the open interval AB at which the instantaneous rate of change is equal to the average rate of change over the interval AB. And now I'm going to show you how to do the mean value. Alright, the mean value theorem. The example I'm going to do is you got to state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval, and if it does, find each value of c in the interval AB that satisfies the theorem. The function that we are using is f of x equals x squared plus 2x minus 1 on the interval 0, 1. So the first step you got to do is plug the x-intercepts into the original function and solve for y. And whenever you do that, you plug 0 into the function and get negative 1. So your x-intercept for that one would be 0, negative 1. Then you plug 1 into the function and you get 2. So those are your x-intercepts. Then you got to find the slope, which is the y2 minus y1 over x2 minus x1. Whenever you're using the x-intercepts for that. Whenever you plug that in, it'd be 2 minus negative 1 over 1 minus 0. You add those two to get 3. 1 for that. So the slope would be 3. The third step is to find the derivative and set equal and set it equal to the slope to find where the slope of the tangent line equals the slope of the secant line. So whenever you find the derivative, you get 2x plus 2. And then you've got to equal that to the slope. And then solve for x. And you will get 2x. X equals 1/2. So that x equals 1/2 is where the tangent line and the secant line are parallel. And then at the very end, you got to write it out to show, write it out in a sentence to explain your answer. And the way you can write that is the slope of the secant line is 3 on the interval 0, 1 when x equals 1/2. The slope of the tangent line equals slope of secant line. And that is how you do the mean value theorem. And now to Bailey with the conclusive concepts of this project.
I'm Bailey, and this is all the conclusive aspects of our project. Here we have our f prime, and we took our denominator and moved them up to the top to get our derivative, and this one's negative, and then our f prime prime is positive. So we took our f of x, and we plugged it in, set it equal to 0, so we have 32 zeros, our x-intercept. And then our y-intercept, we plugged in 0 for all the x's of our f of x, and so we have 0 as our y-intercept. Our vertical asymptote, we took the denominator of our f of x and set it equal to 0, so we got 0 for that too. And then our horizontal asymptotes, we multiplied both sides of the top, or this side, by x squared, so we can make it one fraction. Then we have x cubed plus 32 over x squared. So since the top power is more than the bottom, it does not exist. And then our critical numbers, we took our f prime and set it equal to 0, so we got 0 for that since the bottom is x cubed, so we have 0 for the bottom. Our points of inflection are also 0 because we plugged our 0 in we set it equal to 0 for f prime prime. So since we have 0 for that, we have 0 for almost all of this. So then we have our chart and our graph. For our chart, we took our intervals, which were negative infinity to 0 and 0 to infinity. And when we plugged we plugged in negative 1 and 1 to have numbers that fit inside these intervals, and we have a positive for f prime and a positive for f prime prime. The characteristics of the graph that it shows us is increasing and concave up. And then we plugged in 1, and we have a negative for f prime and a positive for f prime prime. And then we have a decreasing and still remains concave up. That's when we have a concave up on this side, and then we have our vertical asymptote at 0, like we said. And then we have back down, still concave up in our decreasing interval. And that's all for this problem.